Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. So far what we have seen in this course, the mechanic parts, especially the mechanics part, I can clearly say that the kinematics side. So where we have started with the geometrical model, we call forward and inverse kinematics. Then we have started talking about what you call differential kinematics. So where in the differential kinematics we were talking about one important matrix called Jacobian. So after that we have slightly moved away where we have actually touched upon statics. So this particular lecture is going to talk about more, you can say, into a real system, in the sense we are going to talk about dynamics. So the mechanics part is going to end with the dynamics. So what we are trying to see in this particular lecture, we would be seeing robot motion dynamics, not structural dynamics. The structural dynamics we will see in the end. So robot motion dynamics, in that we would be seeing what are the types, and we will see how to derive the equation of motion. In the sense, this particular lecture mainly specific to give introduction to the robot dynamics. The robot dynamics again in the beginning we said, so we can actually write as a motion dynamics and structural. So it is actually structural. So both we are going to see, but this particular lecture is going to talk about more on motion. The structural thing will come in manipulator design aspect. So however, this particular course is mechanics and control, so we would be seeing more on motion. So that is what we are going to give in this introduction. Then this motion dynamics can be classified, or this can be even some people call the equation of motion. So this further classified into two. So that is what we are going to see. So how the forward kinematic model, inverse kinematic model was there. Then we have seen forward differential kinematic model and inverse differential kinematics model. The same way we would be talking about forward dynamics and inverse dynamics, but the scenario is not the same. Okay. So here it is actually mapping between, you can say, configuration space and you can say the joint, or you can say operational space, but here the spaces are different. Okay, that we would be seeing. Then for getting this equation of motion, there are several, you can say, formulation methods. We are going to talk about two popular methods. In that one we are going to see in this particular lecture in detail with an example. Okay. So I hope now you are clear about the structure of this lecture. So we will go further. So you know, dynamics is nothing but study of systems that undergo changes of state as time evolves. So in that sense, the robot dynamics is more general. It would be having, you call, kinematics and kinetics. Okay. So where one with regard forces or efforts, the other one is without, you can say, considering that. But here we are going to call as a general, in the sense you are going to relate the motion, okay, and cause of motion or causes. So this relation we are going to relate, not like simple kinematics. So that's why we always actually robot dynamics, kinematics we will call robot kinematics, but robot kinetics is very rarely people put it forward. So now in that sense, what mechanical system also such as robot, that changes of states involve motion, but what else would be coming? So it actually give signs of motion, but it describe why and how the motion occur. That's what I said. So we are actually relating the input to the output. Okay. So here the input is actually your efforts or causes. Okay, the causes which is causing the motion, and we are actually trying to see the motion relation. So but what it is actually a multi-body system. So we are trying to see how it can be done one by one. So in the sense, when forces and moments are applied on a massive bodies, so how we can actually understand the system of motion. That is what the idea. So why this is actually very important, because this is evolving from, you can say, position. So orientation, that derivative is actually making. That's what I said, F equal to ma, it is actually Newton's second law. But if you take a very general, if you assume that there is a mass, that mass is actually like connected with a spring, that is connected with another spring and a dashboard. So then you can see this would give a frictional component, this will give a restoring, and this will give inertial component, right. In the sense, this same equation F can be written as function of x, x dot, x double dot, right. So this is what we are trying to write, that is what we have written here, okay. So in addition to that, what, so this is actually like mainly to utilize, so two things, so it will actually like give a fundamental equation, but this equation is for control and it can be used for even what you call design the overall system. So if you look at that aspect, so what one we are expect, we are writing a generalized. So earlier I said f can be written as, so function of, you can say x, x dot and x double dot. So this equation we are actually like writing in a generalized manner with a vector. So this is actually tau is the input vector, and this q is actually like, you can say, the joint vector of joint variable, then the velocity and acceleration. In the sense, we are writing a generalized form, okay. So this is more important for one, because this is a nonlinear, so that's why we are writing straightforward. In fact, we have to write strictly, so q, q dot and q double dot comma t, because this is a dynamic system, it is function of time, but we are actually ignoring, because q also function of t, so q dot also function of t and q double dot also function of time, so we are actually like ignoring. Similarly, tau also function of time, okay. So that is the whole idea. So we will actually like see, some people this bigger equation can be reduced into a small, you can say, state space form, that too like we can write as, you can say, acceleration plus other terms. So in the sense, the acceleration coefficient will come as a matrix and this other term as a vector, and this is actually like acceleration vector. That is what we have written here. This is acceleration vector, and the coefficient of acceleration vector is what we are calling as inertial. So this is the inertia matrix, okay. These are all called other effects. Even some people even further this decompose into gravity and other effect. Some people call even gravity frictional other effect. Some people even further go on. So centripetal and Coriolis separate, and you can say friction separate, gravity separate, like that you can actually like make it. But I think we will restrict this up to this, because we are going to do the second part as the simulation side. So I hope this would be very much beneficial, okay. So why this is actually like very important, because it is actually like helpful for analysis and control, and similarly this can be used as a design tool, okay, in order to cross verify your system and further use for design aspect. So that's why this is actually like very important. So now we will actually like see what are the subclasses of robot dynamics. So we have seen tau is actually like function of, so q, q dot and q double dot, right. So these are the thing. So now this is actually like one space which is actually like motion variable, okay, which we simply call system state. So we call state variables, okay. So the other side is actually like what, you can see the input variable, in the sense it is the cause of motion, or you can say simply called the causes, right. So can we map this causes to motion? So in the sense, you take a, you can say a serial manipulator, okay, you connect a motor and you provide a torque, how the system is actually like behaving. So if you look at that, so what you can see, in the sense you are given an input vector, you are trying to find the, you can say q dot, q double dot and q, we are actually trying to find the resultant motion. So in the sense, so these are actually like known states, q dot, q double dot, q, all are actually like we are trying to find out. In the sense, the input is known and we are trying to find out. This is what you call forward dynamics. This is very simple. So you have a motor and give a torque and see the system, or you have a linear motor, so you are actually giving a force and trying to see how the system is behave. The sense it is actually like forward dynamics. So what it is trying to do, it is actually like analyzing in real time, it is actually like analyzing in numerical background, it is actually like simulating, right. So that is what the whole idea, which is very similar to differential kinematics, but differential kinematics is mapping between what, So task space velocity to configuration space velocity, but here it is mapping the input vector to what you call the unknown q double dot, then you can integrate, then q dot will come. Okay. So that's why I said that known state q and q dot, you are trying to find out q double dot. This is forward dynamics. It is very close to open loop, you can say, analysis system, not control. You are actually like giving input and see what is the system output. In the sense there is a football in front of you, you just go and kick, so how the ball is rolling, that is what you are trying to see. So this is actually like something like you have one ball and you are actually like kicking it, so the ball is rolled, that kind of thing. Okay. So this is what you can see simulating or analyzing the manipulator. So obviously the contemporary of this is just opposite side, where the q dot and q double dot would be known, and you are trying to find out what is tau. Okay. So in the sense these are actually like given as a trajectory. So in the sense it is actually like time based trajectory, so which is actually like twice differentiable, in the sense q dot q double dot would be known. In the sense you take a car and you are trying to follow this with respect to time, or in the other sense, so you have a ball, that ball need to go at a certain goal post. Okay. So this kind of thing, in the sense, so how much force or what direction you provide a force, the ball will roll here, right. But the other thing is it is open, you are just hitting and seeing, in the sense you give a known input, known force, and seeing the rolling of the ball, which is forward dynamics. Whereas the inverse dynamics, the ball supposed to go in certain manner, so what force and direction you need to provide. So that is what it is, more or less a small kind of controller, but it is still open loop controller, it is a feed forward. Okay. So that is what we are actually like trying to see. So this is a problem of controlling manipulator, but this is a problem of simulating or analyzing the manipulator. Okay. I hope you would be clear now what is the classification of can say dynamics. Now we will see what are the formulation methods. So there are several methods, as I already mentioned, but we would be taking two popular methods or approaches which would be useful for the equations of motion or equations of motion of a robot or manipulator, which is very common in rigid body dynamics. So one is actually like energy approach. Okay. So the other one is actually like equilibrium approach. Okay. So that is what we are actually seeing it. Okay, or some people call that is momentum approach. So one is energy based approach is Lagrange-Euler, where Lagrange is actually like modify the Euler equation and come up. This is very simple and symmetric in nature, and it actually give much better result for a small, you can say, size of manipulator with very less number of degrees of freedom. Whereas the degrees of freedom is actually like increasing, in the sense the active joints are actually like getting increased. So the Euler Lagrange is not so easy, or Lagrange Euler is not so easy. Okay. And the second thing is, the second one is momentum force approach, where Newton's you can say second law and Euler's you can say equation of motion can be used. So this is very efficient in terms of computational aspect or implementation side, because the derivation is simple, but this would be consist of partial derivative and time derivative, but here there is no derivative involved. Okay. So that's why most of the people uses for real time control the you can say Newton Euler approach rather than the Lagrangian Euler approach. Only issue is this would be having a vector cross product, but it is actually like messy. You have seen already the velocity propagation, right? You have written, so omega 1 to omega n, then v1 to vn. So similarly in this case it's supposed to go a0 to an, then you have to go for the body, then you have to go for acg to you can say ac0 to acn, then you have to go for inertial force, inertial moment. It is actually like lengthy, but computational side, although it's a lengthy, it is actually like very efficient and easy to implement. So let us actually like go to one such method in this particular lecture. The second method we will see in the next lecture. So Euler Lagrange is actually like, as I already mentioned, it is energy based approach, but in the beginning of the lecture itself I said this particular course we are talking about only rigid body. So in the sense we are talking about rigid body dynamics. So since the system is rigid, so what are the energies would be there? So only two kind of energies would be there. So one is kinetic, the other one is potential. Okay. So these two energy, if is there any difference between these two energy, so then there is a motion exists. Even this energy difference, how they have written, so kinetic energy is always upper hand. So kinetic energy minus potential energy, if there is a quantity, that quantity is a scalar. If there is a existence of this quantity, then there is a motion exists. So based on this L value, we can calculate the equation of motion. That is what the Euler-Lagrange or Lagrangian formulation method, some people call Lagrange-Euler method also. Okay, so that is what we are seeing it, right? So now this energy difference, what we are trying to use. So further, the equation is actually like coming based on very simplified manner. The detail is already given in some of the lecture handouts. You can see how this equation has come. Okay, so right now we straight away take this equation. This equation has come from the modified energy, you can say, equation. So you know, if this is 0, so that would be the energy conservation, but right now we are giving the input. That's a modification as done from the energy method. Okay, so now you can see that L is the scalar, but the q dot is actually coming in the other sense. So tau I can write as time derivative of, so dou L by dou q I, okay, dot, this is a dot, minus dou L by, so dou q I, okay. So that is equal to tau I. So this you can recall, this is a vector form I have written, but this is actually like individual element, you have to do it. Okay, so just to give idea, so I am just giving a general expression. So where the kinetic energy would be having two parts. So one is actually like translational kinetic energy, in the sense this is due to the mass. Okay, so then the rotational kinetic energy, that is due to the second moment of inertia. Okay, so or you can say simply inertia. So that is what we are trying to write. So you know, half mv squared is a scalar form, that you want to write it in a vector form. So v transpose m into v, so half would be common. Similarly, if you write I omega squared is the scalar form, so the same thing you write it vector form, omega transpose I is the matrix and omega, so this one. So this is a tensor. Okay, the tensor we would be using it. So that I hope you are already gone through what is tensor. So this is the inertia tensor, and this is the, you can say, translational inertia, which is a mass. As a scalar you can take it out. So one thing you should be knowing, this is actually like Ci with respect to what you call zeroth frame, in the sense the absolute velocity and absolute, you can say, what you call acceleration we would be using further on. Okay, but here it is actually like only corresponding angular velocity, but this is actually like absolute. That is what one supposed to be known. Okay, so let us actually like move further. So this is what the you can say potential energy, which is mgh, but this h is actually like you can write it in a position vector, the vertical axis. Which axis you are considering the gravity, that axis you have to take it. Okay, so now in that sense we will take it one simple example. I assume that this is a mass concentrated, in the sense inertia of these two are actually like 0. This is inertia tensor is 0 tensor. Okay, so you no need to bother about I omega squared and all. So now if you take this, so what one can easily see, so what is x1, so x1 is here, what is actually like x2, that is also clear here, so that we can actually like derive it, right. So this is straightforward. So similarly you can see this is also obtained. Once you obtain, what you can do x1 dot, so y1 dot, similarly x2 dot and y2 dot, and half m x1 m1 x1 dot squared plus m2 x2 dot squared plus m1 y1 dot squared plus m2 y2 dot squared, right. So this you can actually like calculate, and then you can find it. That is what we are trying to do. You can see. So for that you need to know x1 dot, y1 dot, x2 dot, y2 dot. So you know already x1 and x2, y1 and y2. So you can actually like take time derivative. So this is what the time derivative. So that would be function of, you can say, the joint space variable. So now you can actually like substitute that. You will get the kinetic energy in this form, and you can take the potential energy. So here you can assume that the gravity is pulling down. So in the sense the gravity direction coming down. So you can actually like see in that sense. So y1 is equivalent to h, okay, of the first body. So y2 is actually equivalent to the second body, right? So that is what we are actually like trying to write. So you can see like m1g y1, so m2g y2. So that original value we substituted. So now what we got, potential energy we got it, previous slide we got the kinetic energy. Now we take the Lagrangian, which is kinetic energy minus potential energy. This give this a scalar. So now we can actually like substitute the relation. So what relation? If you want to have a tau 1, so tau 1 is time derivative of a partial derivative dou L by dou theta dot 1 minus dou L by dou theta 1. So first we calculate dou L by dou theta 1. So for that you can just recall this is what? So theta 1 dot is in this term. So this term and these terms are 0, right? So in the sense this 2 goes, so this goes out, and here you can see like this theta 1 dot is coming only here, so this goes out. So in the sense theta 2 dot remain, here theta 1 dot remains. So we can see what is that partial derivative, right? Right? So similarly you can take dou L by dou theta 1. So unfortunately here, so theta 1 is here, so theta 1 is here. So in this 2 equation nothing, so you can take it 0, and these 2 equations or these 2 relations are coming. So that is what you can actually like take it. Okay, this is time derivative you have taken. So this is actually like partial derivative, you take a time derivative, and then you can see this is what you can see as dou L by dou theta 1, right? So now this is known and this is known, so you just directly subtract this. So that is what your tau 1, right? So tau 1 once you obtain, so whenever we do, you can actually like cross verify. So what cross verification? You have to see any equation, for example A equal to B plus C plus you can say E into F. So what's supposed to be the units and you can say dimension should be equal. So in this case it's a scalar which is all 1 cross 1. The unit supposed to be match. So this tau is actually like Newton meter, right? So then, so inside any term you take, it should be Newton meter, right? So what this will give? This will give radian per second squared. So in the sense you can actually see what is Newton meter, you can write. So kilogram, right? Meter per second squared into meter. In the sense kilogram meter squared per second squared. So here this is kilogram meter squared and second squared is there. So this is kilogram meter squared and second squared, like that you can see, right? So in that sense, if theta 1 double dot comes, so then you have to see the other side. So some kilogram should be there, some mass, and 2 distances or 1 distance squared should be there, right? That you can cross check. If theta 1 dot squared comes, or so theta 1 dot theta 2 dot comes, so then you can see that this is already equivalent to again radian per second squared. So you can see the same thing supposed to be there, right? You can see 1 you can say mass, and 2 you can say distance. You can get it, right? So similarly here the gravity is there, which is meter per second squared, right? Then you can see like only 1 meter should be there, in the sense 1 length and 1 mass. So you can cross check. So like that you can always cross check, and then you can actually like get it. So when we write it this in a matrix and vector form, even one more check is there, but whenever you get the equation, immediately you cross check the coefficient of acceleration or coefficient of velocity squared or velocity product is getting that ratio, okay? So now in that sense you can actually like go to the next one. So where tau 2, so again dou L by dou theta 2 dot and dou L by dou theta 2, you can get it. So this is the dot you can say partial derivative, and this is the you can say partial derivative with respect to theta 2, and now you can see this, you can take a time derivative, and this minus of this will give tau 2, right? This is what the case. So again you can see this is 1 kilogram and 2 distance, 1 mass and 2 distance, 1 mass and 2 distance, 1 mass and 2 distance, and this is again 1 mass and 2 distance, and this is G is there, so 1 mass and 1 distance, right? So you can actually like cross checked. So this is the way we have actually like derived it. The same manipulator, we can see what is you can say Newton-Euler method, and we can actually like see this example and see whether the equation is coming as similar to this particular method. So, in that sense, the next lecture we would be seeing the other method called Newton-Euler method, and we will see there also the same example. So, with that we will close this dynamics part, then we will go to the equations of motion, where we will write in a state space form, and then in the you can say simulation side we will take more example and we will understand. Okay. So, with that I am closing this particular lecture. See you then. Thank you. Bye.